We're moving on to arctangent. Again, I want to just talk through the definition of arctangent, and then I'll have you pause the video to work out the derivative. As we're talking through these definitions of the inverse trig functions, it sounds like I'm making choices. I'm saying, I like to keep quadrant 1. I like to keep the standard copy of quadrant 1, which corresponds to the interval from 0 to pi over 2. I do like that. If I were free to choose, I would make that choice. I'm actually just matching the standard definitions of these things. So there is a standard domain that we restrict the domain to before we invert it, and that becomes the standard range for the inverse trig functions. So although I'm presenting this as we're making choices, I'm just pointing out that the choices that the mathematicians that have gone before have made are logical. When we get to secant and cosecant are kind of interesting because there are two accepted definitions for those functions. And we'll talk about that more in the next video. But for arcsine, arccosine, and arctangent, there is a standard definition of those so that the range, which corresponds to the restricted domain, is set. Okay, now, if I look at the adjacent quadrants, I know I don't want quadrant 3 because I want to get a connected piece of graph. If I look at the adjacent quadrants, tangent's negative in both of them. But if I look up here, I see that the only way to get a connected piece of graph without having an asymptote smack dab in the middle is to choose the interval from negative pi over 2, that's a 2, from negative pi over 2 to 0, which would correspond to quadrant 4. Okay. So when we restrict the domain, and here, of course, I hadn't drawn the whole thing. I'd just drawn 2 periods worth. But we restrict the domain to just 1 period's worth of the graph, and that's the period between negative pi over 2 and pi over 2. So this is the graph of y equals tangent of x. X is in the interval from negative pi over 2 to pi over 2. So our restricted domain, which will become the range, is almost the same as it was for arcsine. The difference is with arctangent, these endpoints aren't going to be included. And that's simply because tangent is not defined at negative pi over 2 and pi over 2. So we take the inverse of this, and that gives us y equals arctangent of x. Now that is a graph that you should be familiar with, because what happens when we take the inverse is that these vertical asymptotes become horizontal asymptotes. So we've got horizontal asymptotes at heights of pi over 2 and negative pi over 2, and knowing that graph is the easiest way to describe the end behavior, the limits as x goes to infinity or negative infinity, of arctan. Of course, what this means is we get it by simply switching the roles of x and y in the description of tangent with the appropriately restricted domain. So it's x equals tangent of y, with y in the interval from negative pi over 2 to pi over 2. So that's the function that we're working with. So go ahead and pause the video, work out the derivative of that one for me. So once again, I started with the equation that gave me the relationship between x and y, and I took the derivative with respect to x of both sides. So we get 1 equals the derivative of tangent is secant squared, so secant squared y, chain rule, times y prime, which is the derivative of the inside part. Solving for y prime, we get that y prime is 1 over secant squared y, and that's actually never 0. So wherever arctan is defined, it's differentiable. Okay, so then I came over here. Now, anytime I have a trig function squared, there is a Pythagorean identity that gives me the relationship between that and another trig function squared. There are a total of 3 Pythagorean identities. Sine squared plus cosine squared equals 1. And then there's one that gives me the relationship between tangent squared and secant squared. And there's one that gives me the relationship between cosecant squared and cotangent squared. Some of you may have all 3 versions memorized, and that's fine. Some of you might only know the sine squared plus cosine squared equals 1, and that's fine as long as you have a working knowledge of it. I started here with this one, and I said tangent. Tangent has cosines in the denominator. So to get to the Pythagorean identity that has tangent squared in it, I divided through each piece by cosine squared y. And then sine squared over cosine squared became tangent squared. Cosine squared over cosine squared became 1. And 1 over cosine squared is secant squared of y. And that's why secant and tangent are the two that show up in the same identity, because they have the same denominator. They both have a cosine in the denominator. Now this one's super nice because I don't actually have to take the square root to solve for secant, because it was secant squared that I have to substitute in for. So no need to worry about the square root and the absolute value and figuring out the sign of things. This becomes 1 over 1 plus tangent of y, quantity squared. Tangent of y was x, so that's 1 over 1 plus x squared. Pretty cool.